And that can be written as, remember, 1 plus 3 plus 5 up to 2n minus 1 is P of n, right? It's P of n. So P of n equals to n squared. So equals to n squared. So we rewrite this as n squared. Then 2n plus 1, 2 times n plus 1 minus 1, that's 2n plus 1. That's 2n plus 2 minus 1, right? We simplify this, so we get n squared plus 2n plus 1. What is that? That's a perfect square. That can be written as n plus 1 squared, right? So this is the proof. This is to say, add the first n plus 1 odd natural numbers. That is n plus 1 squared. And that's it. That's the whole proof. The n plus 1, just the method of induction. The induction is saying prove the first case, and it's true for 1. Then assume it's true for n. Then to prove n plus 1 step. That's just one of the steps. That's part of the induction method. Make sense? Okay, let's go back a little bit. So what are we proving? We're proving this proposition. The sum of first n odd natural numbers equal to n squared. Yeah. If we write it out, sum of them, so 1, the first natural odd number is 1. 1 equals 1 squared. The first 2 odd natural numbers are 1 plus 3, which is 4. 4 is 2 squared. The first 3 odd natural numbers are 1 plus 3 plus 5, which is 9. 9 is 3 squared. The first 4 odd natural numbers are 1 plus 4 plus 5 plus 7, which is 16. 16 is 4 squared. You see, that fits into this, right? And we add up the n odd natural numbers, that equals to n squared. So we assume the first n odd numbers, the n odd natural numbers equals to n squared is true. So we assume this. This is our assumption. Okay, how do we write out the first? How do we know the last n odd natural number is 2n minus 1? We can figure out from this, right? You see 3 is 2 times 2 minus 1. 5 is 2 times 3 minus 1. 7 is 2 times 4 minus 1. Okay, so the next one would be 2 times 5 minus 1, which is 9. And the next one would be 2 times 6 minus 1, which will be 11, so on and so forth. So the nth odd natural number is 2n minus 1. So we assume this is true. We assume 1 plus 3 plus 5 up to 2n minus 1 equals n squared. Then we use this to prove for p of n plus 1. So n plus 1, p of n plus 1, we read it out. So we want to prove this. P of n plus 1 means 1 plus 3 plus 5, so on and so forth, up to 2 times n plus 1. Because we're adding n plus 1 odd natural numbers. And we want to show that equals to n plus 1 squared. So how do we do that? We read it out, right? We read it out, 1 plus 3 plus 5 up to the n plus 1 odd natural number, which is 2 of n plus 1 minus 1, right? Then that would be the sum of the first n odd natural numbers plus the n plus 1 natural numbers. Okay. Right. So this is the sum of the first n natural numbers. Then this will be n plus 1 natural odd natural number. Right. So by our assumption, the sum of the n odd natural numbers equals to n squared. Equals to n squared. So we simplify this n plus 1 odd natural number. That would be just 2n plus 1, right? So 2 times n plus 2 minus 1. That would be 2n plus 1. And we see this is a perfect square, right? That's n plus 1 squared. That's how we show. So that means the n plus 1 is true. Yeah, that's a perfect algebra calculation. So this is the sum of the first n odd number, odd natural number. And this is n plus 1. So we simplify, that is true, n plus 1 squared. Okay, so this is how we prove the proposition by induction. So the proposition is this. The sum of the first n odd natural numbers equal to n squared. Okay, anyone has any question? Okay, let's see the second one, the second proposition. Okay, let's go over the algebra. Let's think, of course, the first odd natural numbers. Let's think about odd natural numbers. Natural numbers are 1, 2, 3, 4, 5, so on and so forth, right? Then odd natural numbers are 1, 3, 5, 7, 9, 11, so on and so forth. So 1 equals 1 squared, which is true. So 1 plus 3, the sum of two natural numbers is 2 squared. The sum of 3 odd natural numbers is 3 squared. Ada, what do you mean the next proposition? Oh, the next proposition. You mean this one? If n is a natural number, then 5 divides n raised by 5 minus n.
Professor, can you go down a little?
This proof?
Yeah, that one I think he wants.
Oh, okay. Yeah, let's go over this proof. So the proof is basically 3 things involved. So first thing involved is to prove for the basis case, basis case is P of 1. So 1 odd natural number equals to 1 squared. So 1 equals 1 squared, which is true. So we finish with base case. Now the second one is, the second inductive step includes 2 steps. Okay, includes 2 steps. So first we assume P of n is true. What is P of n? P of n is this. 1 plus 3 plus 5 up to plus 2n minus 1 equals n squared. Let's see if this makes sense, right? So the 1 is the first odd natural number. 3 is the second odd natural number. 5 is the third one. And the nth one is 2n minus 1. So the nth odd natural number is 2n minus 1 equals to n squared. So we assume the sum of the first n odd natural numbers equals to n squared. So we assume this. So this is P of n. What do we want to prove? We want to prove Q. So this is like a direct proof. We assume P, we prove Q. So Q in this case is P of n plus 1. So we need to show, well, or we need to prove P of n plus 1 is true. It's true, which means 1 plus 3, 1. We want to show this. We want to show 1 plus 3 plus 5 plus 2n minus 1 plus 2 of n plus 1 minus 1 equals to n plus 1 squared. So this is what we want to show. Okay, so how do we show this? Some algebra. The sum of n plus 1 natural odd numbers is this. It's the sum of the n odd natural numbers, right? 1 plus 3 plus 5 up to plus 2n minus 1. So this is the first n odd natural numbers. So then we add one more, the n plus 1 odd natural number. So 2 times n plus 1 minus 1. So this is the n plus 1th odd natural number, right? By assumption, the sum of the n odd natural numbers equals to n squared. We assume this. All right. So now, so the n squared plus the n plus 1 odd natural number. We simplify, we get n squared plus 2n plus 1, which is n plus 1 squared. Does this make sense? How does 1 plus 3 plus 5 plus 2 plus 1? Oh, think this way. Think you're adding. Okay, so what? So the sum of n plus 1 odd natural number what's that? It's 1 plus 3 plus 5 plus plus 2n minus 1 plus 2 of n plus 1 minus 1. Right? The sum of n plus 1 are the natural numbers. So 1 plus 3 plus 5 plus plus 2n minus 1. 2n minus 1 is a representation of nth odd natural number. Then what's the representation of n plus 1 odd natural numbers? 2 of n plus 1 minus 1. Right? What about next one? So what is n plus 2? The next one would be 2 times n plus 2 minus 1, so on and so forth, right? Then the next one would be 2 times n plus 3 minus 1, so on and so forth. So this is just representation. So 1 plus 3 plus up to 2n minus 1 is the first n odd natural numbers. Then we need to add one more. We need to add n plus 1 odd natural number, which has presentation of 2 of n plus 1 minus 1. Then we simplify this, so we get in the end, we have n plus 1 squared. Any questions? So basically, this is the whole proof. So base step, then assume P of n is true, prove P plus n is true, P of n plus 1 is true. So this is called induction proof. The basis case and P implies Q. We assume P, we prove Q. Let's see the next proposition. So n, again, we assume n is a natural number. Then we want to show 5 divides n raised by 5 minus n. Okay, let's try for the first case, basis step, P of 1. So let's see 5 divides 1 raised by 5 minus 1. Well, 1 raised by 5 is 1. 1 minus 1 is 0. Right? 5 divides 0. Right? That's true. Because 0 divided by 5 is still 0. So inductive step, we assume P of n is true. Oh, you know what? I use K. If I make this lecture notes, I would use K instead of n, because this n, you know, might be confusing with this n, right? Because I would like to use K. I would say assume P of K is true, then prove P of K plus 1 is true. Okay, don't get confused with those n's, all right? They're just a variable. But normally, right, if I do this lecture notes, I would use another variable. So in this inductive step, we assume P, we prove Q. So basically, we have statement P implies Q. So we assume this. We assume 5 divides n raised by 5 minus n. Then we want to prove for n plus 1 case. What's n plus 1 case? N plus 1 case is this. N becomes n plus 1. So n plus 1 raised by 5 minus n plus 1. So now we need to do a little algebra. So let's see, what is n plus 1 raised by 5 minus n plus 1? So n plus 1 raised by 5 minus n plus 1. If we remember, we learned Pascal's triangle, binomial theorem, we could use here, right? N plus 1 raised by 5 the coefficient of the first term would be n choose 0, which is one way. The coefficient of the first one would be 1. Then the coefficient of the second one would be n choose 5. Out of 5, choose 1. How many ways? 5 ways. Right? Then this would be 5 choose 3. 5 choose 3 is the same as 5 choose 2. Right? So we get these coefficients. We get 1, 5, 10, 10, 5, 1. Right? Then the first term, n, goes to descending order. So have n raised by 5 for first term, n raised by 4 for the second term, n raised by 3 for the third term, n squared for the fourth term. You know, this is n. Then the last term has no n in it. We can think as n raised by 0. N raised by 0 is 1. And then the second term goes ascending order. But however, here just 1. Multiplied by 1 doesn't change anything. But if the second term is something else, it just goes ascending order, right? So we're expanding a plus 1 raised by 5, we get this. We get n raised by 5 plus 5n raised by 4 plus 10n cubed plus 10n squared plus 5n plus 1. So this is expansion of n plus 1 raised by 5. Now minus n minus 1, right? So simplify 5n minus n, 5n minus n, that becomes 4n, but anyway, we don't have to do that. So the second, look at the second one. So we moved minus n to go with n raised by 5, so we have n raised by 5 minus n. Then plus 5n raised by 4 plus 10n raised by 3 plus 10n squared plus 5n, because 1 minus 1 becomes 0. Right, 1 minus 1 becomes 0. So now, so remember n raised by 5 minus n, we assume that, remember here, we assumed 5 divides n raised by 5 minus n, which means 5 is a factor of this, which means n raised by 5 minus n can be written as 5 times another integer. Right? 5 is a factor of the right-hand side. That means the right-hand side can be written as 5 times the integer. So let's write 5k. K is some integer k, right? So this is by assumption. So n raised by 5 minus n can be has a factor of 5. That means this term can be written as 5k. So now we see 5 is the coefficient of every term. That means we can factor out 5. We factor out 5, then we have 5 times and some integer. Because k is an integer, n is an integer, so every term is an integer, adds up, still integer. So that means 5 is a factor of this term. Right? That means this term, that means 5 divides this term. So thus, so conclusion is 5 divides n plus 1 raised by 5 minus n plus 1. So which is the statement we prove? Which is the Q statement? We prove. So which means P of n plus 1 statement is true. And that's the whole proof. So the first step is to show for 1 works for 1. Second step, assume works for n. To prove it works for P. To prove it works for n plus 1. And the algebra is here. Okay, anybody has any question? Okay, let's see next proposition. So the summation of 2 raised by k, k from 0 to n minus 1. So you can think about a 2 raised by 0 plus 2 raised by 1 plus 2 squared plus 2 cubed plus 2 raised by 4 plus 2 raised by 5, so on and so forth, equals to 2 raised by n minus 1 for all natural numbers. Or we can write this way. 2 raised by 0, 2 raised by 1, 2 raised by 2, up to 2 raised by n minus 1 equals to 2 raised by n minus 1. All right. So the summation is a shorthand. So summation here is a shorthand for this. Right. Okay, let's prove for base case. So let's see n equals to 1, right? N equals to 1, we see this is from 0 to 0, right? 1 minus 1 is 0. So 2 raised by 0, which is 1, equals to 2 raised by 1 minus 1, which is 2. So the basis step is true. Right? Now we assume it works for n. Better to say it works for k. So assume 2 to the 0 plus 2 to the 1 plus the 2 squared, so on and so forth, up to 2 raised by, maybe some of you think of this k minus 1 better, equals to 2 raised by k minus 1. Then we want to show, so this is assumption, so this is p, right? P implies q, q is this n plus 1. So we want to show 2 to the 0 plus 2 to the 1 plus 2 squared, so on and so forth, up to plus 2 raised by n minus 1 plus 2 raised by n plus 1 minus 1 equals to 2 raised by n plus 1 minus 1. Okay, 1 is minus 1 happens in the exponent, but here x minus 1 is in the base. So now we need to calculate. We need to calculate. So we need to calculate this what do you call it? This left-hand side. All right. So let's calculate this left-hand side. Well, 2 raised by n plus 1 minus 1, that is just 2 raised by n, right? 2 raised by n. So let's add up 2 to the 0 plus 2 to the 1 plus 2 squared plus plus 2 raised by n minus 1 plus 2 raised by n. Right? The term before 2 raised by n is 2 raised by n minus 1. By our assumption, 2 to the 0 adds up to 2 raised by n minus 1 equals to 2 raised by n minus 1. Then we plus 2 raised by n. Right? So we have 2 raised by n plus 2 raised by n. We have 2 of 2 raised by n minus 1. What's the 2 times 2 raised by n? That can be combined the exponents. That's 2 raised by n plus 1. Right? So that equals to 2 raised by n plus 1 minus 1. So we proved it's true for n plus 1. And that's it. That's the whole proof. Okay, proof for the base case, n equals to 1. Then we assume it's true for n case. Then we prove it's also true for n plus 1 case. Anybody has any question? Okay, let's read her remark. Yeah, this is a step is always first. Pn, we assume Pn. The step is to prove, to show it's true for P of 1. And second step, assume P of K. I like to use P of K. Then to prove for Q, Q is P of K plus 1. I like to see 3 steps, all right? Okay, let's read her remark here. As with all proofs of conditional statements, when you are trying to show R implies S directly, it's important to not assume that S is true. In the inductive step, where you are trying to show P of N implies P of N plus 1, it's important not to assume that P of N plus 1 is true. I see. Okay, this is not important. So any questions? So 3 steps, right? You prove it's true for the first case. You know, here for most mathematics, because all those in the number theory, you prove it works for number 1, n equals to 1, because we're talking about natural numbers. What's the first natural number? First natural number is 1. So that's why here 1 becomes the base case. But there are other proofs can be done using inductions. Like remember one time we proved by contradiction for there are infinite many prime numbers, right? We can also prove by induction. But the prime numbers, the base case is not 1, right? Because the very first prime number is 2. So the base case doesn't mean time is 1. It could be some other things. But here, for those 3 examples, we are working with natural numbers because we limit n as a natural number. So for a natural number, the first number is 1. So that's why in here, for the 3 cases, we use 1. We use P of 1. So I'm just telling you P of 1 is not for all other proofs. Okay, it depends on the context. So the second step is to assume it works for K. Normally we use K, we don't use this N because it's kind of confusing, right? In the proposition, it's N. Then in the proofs, usually we don't use N anymore. We just use K. So the second step is to assume. We assume the proposition is true for K. Of course, K is a natural number, right? Then what do we have to do? We prove it's true for K plus 1. Remember, K is a random number, right? K is just arbitrary number. So that means, if we assume it works for K, it works for the next one. So that's how the proof is being done, all right? Basically saying, if it works for the basis number, then it works for an arbitrary number, then it would work for the next arbitrary number. So that's the induction proof, induction step. All right, any questions? Okay, let's see the exercise. Probably the exercise is the same. Yeah, exactly the same thing. Oh, there's more. Additional problem is different. Okay, good. Let's try this. Let me share. Okay, try on your own. So this will help you to understand the proofs. Those mathematical proofs are very rigid. You know, it's very rigid. So we have to go along with the steps. As I said before, it's a language between mathematicians or logicians, or anyone who works with mathematical proofs. But remember, you have 3 steps. Okay, so first step to show P of 1. Second step, assume P of K or P of N. Junqi, you're missing P of 1. Now, Moises, assume if you want to assume n equals k plus 1 is true, if you assume k plus 1 is true, you need to show p plus 2 is true. You want to say, okay, assume n equals k, then show k plus 1 case, p of k plus 1. Okay, Xiaomin looks good. The order matters. P of 1 always goes first, then k plus 1. So base case, assume k case, prove k plus 1 case. Okay, what about Aidan, Ajaya, George, Ishrat, Maria, Michael, Mayu, Patrick, Shamisha, Samuel.
To type fast.
Samuel is good. I'm sorry?
It's hard to type fast. The math
I see.
the
I
math
see.
like in the with the cursor.
I see. Okay. Yeah, take your time. And Xiaomin. Alright, then first step is prove 1, right? So prove n equals 1. Second step, assume n case is true or k case is true. So that's just one sentence. Assume, P of n is true. Whatever the P of n is. P of n here is the sum of the first n odd natural numbers equals n squared. There's a 1 plus up to 2n minus 1 equals n squared. Suppose that one is true. Then to prove n plus 1 case. Why do we need to show P n plus? That's how induction proof works. That's how induction proof works. 3 steps. Prove for the base case, assume k case, prove k plus 1 case. Steps. Okay, prove P of 1, assume P of k, prove for P of k plus 1. You use k plus 1. You use k case, right? Then you assume for k case. You assume for k, you assume P of k and use it for P of k plus 1. Whoa, Maria, what are you typing? You're typing 2n plus 1 equals n squared. That's totally wrong. 2n plus 1 equals n squared only works for certain numbers. All right? No, it doesn't work for any number actually. P of 1 equals 1 squared. No, P of 1 doesn't equal to 1 squared. Remember, P of 1 is a statement. P of 1 means, okay, P of 1 means this, means a statement. Means n equals to 1, 1 equals to 1 squared. Right? That's P of 1. P of 1 is a statement. It's if n equals 1, 1 equals 1 squared is true. Then assume P of n. Assume P of n. Assume P of n, which is 1 plus 3 plus plus 2n minus 1 equals to n squared. Okay, assume this. Assume P of n. P of n is a statement. What's the statement? The statement is 1 plus 3 plus plus up to nth odd natural number with 2n minus 1 equals to n squared. Then to prove P of n plus 1. You need to iterate. You need to show P of 1 is true. You need to write it out. Great. Okay, I like what to write the rest. Iterate. I like you write down the k plus 1 term is this. Right, then the sum of the k plus 1 odd natural numbers is that. Then P, remember the statement P is a capital letter P. All right, use capital letter P. Okay, looks good. Just read more about the P of 1. P of 1 is a statement. Right, so either you wrote, so 1 is the P of n, right? P of n is a statement saying 1 plus 3 plus 5 plus 7 plus plus 2n minus 1, not 2n plus 1. Nth, right here, nth odd natural number is 2n minus 1. Think about 3. 3 equals to 2 times 2 minus 1, right? Think about second. So second odd natural number. Odd natural number is 3, right? 3 equals to 2 times 2 minus 1. What about third? Third odd natural number is 5. 5 equals to 2 times 3 minus 1, right? So nth odd natural number is 2n minus 1. What about n plus 1? N plus 1 odd natural number is 2 of n plus 1 minus 1, which is 2n plus 1. Okay. Yeah, P of 1 is a statement. Is n equals to 1, 1 equals to 1 squared. Okay, if you finish the first one, you can try to. No, it's right. P of 1 is a statement. Use a capital letter P. So P of 1 is a statement. What is the statement? The statement says if n equals to 1, 1 equals to 1 squared, which is true, right? Which is true. That's how you prove P of 1. P of 1 is not a natural number. P of 1 is a statement. So to prove n works for 1. No, P of George, P of 1 does not equal to 1 squared. P of 1, as I typed in there, P of 1 is a statement. See the time signature 1:58 p.m. All right, you have this weekend to work on this. Probably this feels very odd for you. By the way, I know some of you haven't taken calculus class yet. The final exam has something with differentiability. So differentiable. I talked to the coordinator. She does not want to change the final exam. So you just have to remember, when we talk about a function, so this is a true statement. If a function is differentiable, it is continuous. Okay. Differentiable means we can talk about the change of the function. Okay, Patrick has written, you mean 1 equals 1 raised by 2. Use the upper arrow to raise. Yeah. So which is true? Then we assume P of n is true, which means 1 plus 3 plus 5 plus plus 2n minus 1 equals n squared. Then we want to prove P of n plus 1 is true, which is 1 plus 3 plus 5 up to 2n plus 1 minus 1. Yeah. Then that can be simplified as n squared plus 2n minus plus 1. That's n plus 1 raised by 2. That's right. Right. Something just like that. Yes.
How do you write the conclusion again?
The conclusion is this is proved by induction. The conclusion is therefore the proposition is true. Yeah. As long as you showed the base case, you assume the nth case, you proved n plus 1 case, you're done.
Okay.
Yeah, solution for homework 10. Let's see, I'll post. Okay, when do you want me to post the homework 10 solution? Let's agree on the time. Because once I post the solution, I won't accept the homework anymore. So how long takes you to finish homework 10? So next Monday, so maybe by Sunday night or Sunday afternoon, let me know a time. Jinqi, you're missing a base case. You're missing P of 1. Or Shamisha, you like to make a function, huh? Then why do we have to do P of n plus 1? That's a super important step of induction proof. Okay, it's just like you're asking me why my name is Chen. That's how my parents named me. Why do we need P of n? Why do we need to show P of n plus 1? Because that's the one step of induction proof. Don't ask why, just follow it, because that's the part of the induction proof. P of 1 is a base case, basis step. Okay, Sunday afternoon. All right, I'll post a solution Sunday afternoon. So you have a Sunday night and Monday morning to study for it. Okay, Moses proof looks good. What? Okay, this is unnecessary. P of n is true implies that there is an m in there. No, that's just for n, right? This is for n. So right, you need to change n plus 1 to be n. P of n is true implies there is an m in the integer such that n raised by 5 minus n equals to 5m. That's not n plus 1. Because you need to show n plus 1. Yeah, for every induction proof, you need 3 things. You need to prove P of 1, then assume P of k, prove P of k plus 1. Or 10, I'm going to post later. So the solution for homework 10 will be posted later today, after this class. 11, I'm going to post on Sunday afternoon, so you have time to finish your homework. Okay, some news looks okay. All right. So let's try 3. Let's try 3 and additional problems. So hopefully we can finish. We have 2 additional problems. Let's try 3 first. My rule, we do not assume the proposition is true. Okay, we're proving by induction. We prove P of 1 statement is true, like you showed. So we assume P of n case, then to prove P of n plus 1 case. Assume P of n case. Better to say P of k case. Right, and then you need to show P of, right, you need to show 5 divides that. Okay, you need to show your third line. You need to show P of n plus 1 is a true statement, which means 5 does divide n plus 1 raised by 5 minus n plus 1. So the rest of it, we just need to do the algebra. Lino, I don't really understand what you. Yeah, you guys can take a look of Moises' solutions. Really nice. He said prove by induction. P of 1, right? He made bold. Very nice. P of 1 is 2 raised by 0 equals to 2 raised by 1 minus 1. So this is here, n equals to 1. So base case. Then he said assume P of n. What's P of n? P of n is 2 raised by 0 plus P raised by 1 plus 2 raised by n minus 1. You're missing something, Moises. P of n is a statement equals to, so missing equals to the right-hand side. What's on the right-hand side? The right-hand side should be 2 raised by n plus 1 minus 1, right? Then to show p plus 1 case, p of n plus 1 case. And also p of n plus 1, you need to write down the second to the last line as equals to 2 raised by n plus 1 minus 1. Because it's in the form of 2 raised by n minus 1, right? So you need to write down in the form 2 raised by n plus 1 minus 1. Xiaoming, you're not using P of n plus 1 to prove. You use P of n to prove P of n plus 1. Okay, the algebra is good. Yeah, Samuel, there's some typos in your answers. It's 2 raised by. Lino, you're trying to write with epsilons? What do you mean? We don't use epsilons in this kind of proofs. There's no epsilon in this kind of proof. Okay, for you guys finished, try additional problem, number 1. Try 1 and 2. Same thing, right? Show P of 1 is true. Assume P of n. Then use your assumption P of n to prove for P of n plus 1. P of 1 is true, right? Assume P of n. P of n is not a statement, right? It's a 2 raised by 0 plus 2 raised by 1 plus 2 raised by n minus 1 equals to, all right, let me write P of n for you. P of n, this is for ident, all right? P of n is this, 2 raised by 0, 2 raised by 1 plus da 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 plus 2 raised by n, 2 raised by, let me use parentheses, n minus 1 equals to 2 raised by n. So this is P of n. 2 raised by 2 to the power 0, 2 to the first power, so on and so forth to 2 to the n minus 1 power equals to 2 raised by n minus 1. Then you want to use this assumption to prove for n plus 1. To prove for n plus 1 is some algebra. Yeah, Ishrat looks good. Michael, you need to write down P of n, where you get 2 raised by 0, 1 equals 1, which is true, right? Then you need to assume P of n. And also P of n is a statement. It's not an expression, it's an equation. And to prove P of n plus 1. Therefore, P of n plus 1 is true, all right? P of n is a statement. In this case, it's an equation. An equation is a statement. Maria, P of 1 equals to something doesn't make sense. P of 1, capital letter P of 1 is a statement. It's an equation in this case. Before P of n, you have to say assume P of n is true, all right? You have to say assume P of n is true. You write down the equation. Then you use the equation to prove n plus P of n plus 1. It's okay. I thought it was a typo. Yeah, there are the many propositions for natural numbers. Because these two additional problems, there's one course for mathematics majored. It's called number theory. So dealing with all these kinds of equations, formulas, usually proved by, because we're dealing with natural numbers, usually we like to prove by induction. So I'm going to show this additional two problems. Okay, let's move to the whiteboard. So the first one is proposition 1 plus 2 plus 3 plus up to n natural numbers. So n represents a natural number. For any natural number n. 1 plus 2 plus 3 plus up to n equals to n times n plus 1 divided by 2. Okay, there's a story in math. It's a great mathematician called Gauss. When he was about 5 years old, his teacher asked the class to add 1 to 100. Add all the natural numbers from 1 up to 100. He answered in a second. He said, that's 5,050. Then the teacher asked him, how did he do that? He said, oh, okay, I just pair them up. Because 1 plus 100 is 101. 2 plus 99 is 101. Then 3 plus 98 is 101. And how many of them? Because I'm pairing them up, totally I have 100 numbers. That just means I have 55 of those 101. So you multiply 50, so 50 of this 101. So you multiply 101 with 50, of course you get 5,050. So basically this proposition is saying that, it's n times n plus 1 divided by 2. But let's prove by induction anyway. So prove by induction. All right, 3 steps. First step, P of 1. Remember, P of 1 is a statement. P means a statement, right? P of 1. So for n equals to 1. So 1 equals to, so let's calculate n times, so 1 times 1 plus 1 divided by 2, which equals 1, right? So this is saying P of 1 is true. And we prove for base case. Base case is n equals to 1, because we're dealing with natural numbers. The smallest natural number is 1. So for n equals 1, we calculate this side. So 1 times 1 plus 1 divided by 2 equals 1. So P of 1 is true, right? So it works for 1. So the proposition works for 1. Now assume P of n is true. That is 1 plus 2 plus 3 plus plus n. Let me use k plus k. Let me use p of k plus k equals to k times k plus 1 divided by 2. Okay, I'm assuming p of k is true, which means when n equals to k, it's a true statement. I want to use this assumption to prove for, and we want to use p of k to prove for p of k plus 1. Right, so how are we going to use that? Right, so now n times n plus, so now n equals to, think about n equals to k plus 1. Right, think, let me write here. So for, let's see, for n equals k plus 1, n times n plus 1 equals to k plus 1 times k plus 1 plus 1. Okay. Let me divide by 2. Divided by 2. Divided by 2. That equals to, let's simplify a little bit. That equals to k plus 1 times k plus 2 divided by 2. Right? So we want to prove p of k plus 1 is true, which means we want to show 1 plus 2 plus 3 plus up to plus k plus up to k plus 1 equals to k plus 1 times k plus 2 divided by 2. All right, so let's do some calculation. So 1 plus 2 plus 3 plus plus k plus 1 equals to, well, 1 plus up to k give us k times k plus 1 divided by 2, right? Then plus k plus 1. So this left-hand side, I'm adding up 1 up to k plus 1. And I know by assumption p of k, 1 adds up to k is k times k plus 1 divided by 2. Now I'm adding k plus 1 term to it. Well, let's simplify this. So k times k plus 1 divided by 2, add the second term. Now I'm going to multiply 2 over 2 for the second term. That's 2 of k plus 1 divided by 2. Right, I'm just simplifying the right-hand side. I need, because I have denominator of 2, so the second term, I'm multiplying 2 over 2. Now I can combine them. So k times k plus 1, so this becomes k times k plus 1 plus 2 times k plus 1 divided by 2. Okay? Both has a denominator 2. I can add up the numerators. The numerator becomes k times k plus 1 plus 2 times k plus 1. Well, both term has a k plus 1 in it. I factor out k plus 1. K plus 1. What's left for the first term? That's k. What's left out for the second term? That's 2. Divided by 2. Now, bingo. You see this? Here, for, let me use this. On this line, when n equals to k plus 1, the right-hand side give us this, right? And from the left-hand side, I add up 1 up to k plus 1 term. I also have this. So this equals this. So here I can put equal sign here. So this equals to above. This equals to above. This equals to above. And then we say here equals to this, right? You see that both sides are equal now. So this is the P of K. So P of K is proved. So this shows P of K plus 1. P of K plus 1 is true. So by induction, the proposition is true. All right. Let's go back to check the step. First step, right? Baby step, basics, the base step. And 2, assume. Okay, I'll go there, Samuel. So the basic step for n equals 1, the statement 1. So for n equals 1, 1 equals to 1 is true. The second step, assume P of K is true. What does that mean? That means 1 plus up to K term equals to K times K plus 1 divided by 2. Okay, this is the assumption. We're going to use this. We're going to use this assumption. We don't need to prove it. We're going to use this assumption. So we want to prove a P of K plus 1. That means we need to add up from 1 up to K plus 1. Okay, from 1 up to K plus 1, we have to go through 1 plus K, then plus K plus 1. Well, 1 add up to K is our assumption, right? Our assumption says equals to this. So substituting into K times K plus 1 divided by 2. We're using this assumption. Then we add K plus 1 term. Then we simplify this, right? So the first term divided by 2, the second term we need also divided by 2. So we multiply this second term 2 over 2, because we can only multiply by 1. And this 1 is 2 over 2. So this second term becomes 2 times K plus 1 divided by 2. Now the two terms have a common denominator of 2. I can add up the numerators. So the numerator for the first term is K times K plus 1. For the second term is 2 times K plus 1. Do you see K plus 1 is a common factor of these two terms? So I factor out K plus 1. Then what's left for the first term? That's K. What's left for the second term? That's 2. So this simplified to be K plus 1 times K plus 2 divided by 2. Right? And this is exactly the K plus 1 times K plus 1 plus 1 divided by 2 term. So this shows P of K plus 1 is true. So by induction, the proposition is true. So this is a step 3. Okay, for n equals to K plus 1. You see, so n equals to 1 is the basis, is the base case. N equals to K is assumption. Then we use this assumption to prove n equals to K plus 1. All right, anybody has any questions? In this case, by induction, we proved it works for all natural numbers. So we show for n equals to 1, we assume n works for K. Then we show it also works for K plus 1. This step is called induction. So in the end, the conclusion is P of k plus 1 is true, so by induction, the proposition is true. Anybody has any questions? Okay, now let's do the second one. Are we ready for the second one? So I'm going to delete this, okay? The second one additional problem is proposition. Oops, let me use black color. So proposition 3. So for any n, for any natural number n, 3 divides n cubed plus 5n plus 6. Okay, so this is our proposition. For any natural number n, 3 divides n cubed plus 5n plus 6. All right, we do the same thing. Okay, so we want to show P of 1 is true. Then we assume P of n is true. They use P of n to show P of n plus k. Let's use k. K plus 1 is true. P of k. Okay, so this is our thinking process. All right, we want to show P of 1 is true. Then we assume P of k is true. And then we use P of k to show P of k plus 1 is true. All right, let's show. So first, let's show P of 1. So to show P of 1 is true. So how do we show that? So when n equals 1, so for n equals 1, so let's evaluate n cubed plus 5n plus 6. So n cubed plus 5n plus 6 equals to, now n equals 1, right? So 1 cubed plus 5 times 1 plus 6. So that means 1 plus 5 plus 6, that's 12, right? And of course, 3 divides 12. So P of 1 is true. Okay, so first step to show P of 1 is true. What's P of 1? P of 1 means 3 divide when n equals to 1, and the proposition is true. So for n equals 1, n cubed plus 5n plus 6 equals to 1 cubed plus 5 times 1 plus 6, which equals to 12. And obviously 3 divides 12, so P of 1 is true. Now, second step, assume P of k is true. That is 3 divides k raised by, let me use parentheses, k raised by cube plus 5 times k plus 6. Okay, so that's our assumption. So when n equals to k, the proposition is true. So what does that mean? That means 3 divides k cubed plus 5k plus 6. Okay, 3 We want to put step 2 into use in step 3. So we to show P of k plus 1 is true. That means that is 3 divides parentheses k plus 1 raised by cube plus 5 times k plus 1 plus 6. Okay, so step 3, we need to show this. We want to show P of k plus 1. That means for n equals to k plus 1. So n becomes k plus 1. That means 3 divides k plus 1 cube plus 5 times k plus 1 plus 6. Make sense? So this step means n equals to k. And this step here, n equals to k plus 1. That's why it's called induction. That's why it's called induction. So this one is n equals to 1. N equals to 1. So n works for 1. N works for k assumption. Then n works for k plus 1. K is arbitrary, right? If n works for arbitrary, also assume n works for arbitrary k. Then if n works for the next arbitrary number, so this is the induction. All right, let's go back to 3. Let's see how do we show 3. We evaluate so for n, for now, for n equals to k plus 1, we just substitute into the expression, right? So n raised by 3 plus 5n plus 6 becomes k plus 1 raised by 3 plus 5 times k plus 1 plus 6. Right? For n equals k plus 1, we just substitute n into k plus 1. Now just do the calculation. So that equals to, for k plus 1 cube, let's use binomial theorem. That's k cube. Hold on 1 second. We want to use, right? We want to use the 3 divides k cube plus 5. We want to use P of k. All right. So let's do that. So that we get k raised by 3 plus 3k squared plus 3k plus 1. So this is expansion of k plus 1 raised by 3. Then plus 5 times k, that's 5k. Then plus 5. Then plus 6. Right? I just expand the first k plus 1 cube. That's k cube plus 3k squared plus 3k plus 1. Then 5 times k plus 1 becomes 5k plus 5. Then plus 6. Now, let's, from here, let's divide it into 2 parts because we want to use P of k. P of k is k raised by 3 plus 5k plus 6, right? So then let's write the rest. So we have 3k squared plus, we have 5k there. We still have 3k. Then we have 6 there. We have 1 plus 5, so 1 plus 5. I basically just rewrite it. I basically just reorganized. You see, I have k cubes. Hold on. I have k cube here, right? I have k cube here. I have 5k here. I have 5k here. I have 6 here. I have 6 here. Why do I want to do that? Because k cube plus 5k plus 6 is from the assumption since 3 divides this 3 term. So that's why I want to use step 2. So I put this together, right? I know this can be written as a 3 something. Let me change to be black color. Because this 3 divides by this, right? This can be written as k cubed plus 5k plus 6 equals to 3m for some integer m. Okay, this is what it means. 3 divides this expression. That means this expression can be written as 3 times something. So 3 is a factor of this expression. So now let's just write these 3 terms as 3m, right? Then add the rest of it. Add the rest of it, I have 3k squared plus 3k. Well, 1 plus 5 is 6. And now let's factor out 3. So let's factor out 3. That's m plus k squared plus k plus 2. Bingo, right? So that means, this is, this already tell us. This means, let's write here. This means 3 divides, this means p of k plus 1 is true. So the proposition is proved. Just do a little, so use step 2 to do the algebra for step 3. Any questions? Two and 3 is the direct proof. You're right. 2 and 3 is exactly some p implies, so 2 implies step 3, all right? You're right. So step 2, right, we're using this. So we're assuming step 2, we prove step 3. That's a direct proof. You're right, Moises. Okay, any other questions? All right, so a post solutions for homework 10, and by Sunday afternoon, so hopefully you finish homework 11. Just by trying homework 11, you'll get credits. They'll post homework, right, solution for homework 11, and I'll see you on Monday then. Okay, question from 9, homework 9. All right, what's your question, Aidan? Homework 9. Nine B. 9, homework 9. Oh, this B, proposition, suppose A, B, C integers. If A does not divide B, C, then A does not divide B, right? Prove by contrapositive. Prove by contrapositive. So same to say if A does divide B, then A does divide BC. Remember that, contrapositive? So treating A does not divide BC as P, then A does not divide B as Q, then we negate Q to show negating P. So negating Q means A does divide B. Then we want to show A divides BC. Okay, we prove by contrapositive, right? So assume A divides B to show A divides BC. A divides B means B can be written, let me follow your notation. B can be written as AK for some integer K. Right? Then BC equals to, as you write, AKC. Right? That shows A divides BC. Yeah, you're right. Huh? How? Okay. A divides B means B can be written as AK, right? Now what about BC? How can you write BC? BC can be written as AKC, right? So that means A is a factor of BC. Do you see that? A is a factor of BC is exactly same by notation, just means A divides BC. That's it. A is a factor of BC. That means A divides BC. Just notation. Does that make sense? A divides B means B can be written as AK for some integer K. Then BC can be written as AKC. And this is exactly saying A divides BC. On the final 6 big questions, 6 different kinds of type of questions, and under some questions there are A, B, C, D different parts. Okay, any other questions? There's no extra credit on final. The final is made by the coordinator. Okay, oh, there's no mysterious coordinator. Remember the midterm exam, her name is written up there, Tatiana. Yeah, she likes to write things out. She's very responsible. I would say she's sometimes she could be a little bit over responsible, but she works really hard. I really admire her. You know how hard she works, how hard she tries to organize. But of course, when you have too many things to do, you make mistakes. Oh, okay. You had her last winter session for which course? Oh, I see. Yeah. She's very detailed. She's very, yeah, I like to have her as my coordinator because it saves me a lot of time. Okay, any other questions? Okay, if no questions, I see you on Monday, all right? The exam will be, similar to the midterm. Okay. Same time, same class time. Okay, good weekend. Have a good weekend.